Welcome back to today's Explainer, where we're diving into Lesson 22 of the GD&T Master Course. Today, we are bridging that absolutely crucial gap between your pristine, perfect CAD models and the very real, often kind of messy world of physical inspection tooling. We're going to focus entirely on translating your design intent into functional gauging design and really mastering those virtual condition applications.
Okay, I want you to picture this nightmare production scenario for a second. You're manufacturing a critical automotive component, and your line is just spitting out 10,000 parts every single day. How on earth do you inspect all of those? I mean, if you think you're going to set every single one of those parts on a coordinate measuring machine and measure every individual dimension, you are going to grind your production line to an absolute halt. It's literally impractical. So what's the actual solution for mass verification?
Well, here's our roadmap to figure that out. We're going to look at why functional gauging exists, break down the virtual condition math, design some gauges, look at actual production workflows, compare these gauges to CMMs, and then finish up with common industry mistakes.
Part 1. Why functional gauging exists, the high-volume manufacturing hero.
Listen, the functional gauge is truly the unsung hero of mass production. Once you leave the prototyping phase and hit high volume, your priorities shift dramatically. You suddenly need extreme speed. Functional gauges give you a super simple binary result: pass or fail. A gauge doesn't care exactly how far off a dimension is. It just instantly checks whether a part satisfies its mating requirements. If the part fits the gauge, it's going to fit into the final assembly. Period. This gives you incredibly high repeatability, drastically cuts down your inspection cost per parts, and instantly verifies that your part will actually function out in the real world.
Moving on to Part 2, understanding virtual condition and calculating that worst-case boundary.
Right, so to design a physical tool that actually provides that instant pass or fail, we absolutely have to nail down the underlying math. And that brings us to the virtual condition. This represents the absolute worst-case scenario envelope boundary of a feature. It combines both the feature's size tolerance, your standard plus or minus, and any geometric tolerances applied at maximum material condition, or MMC, or least material condition, LMC. Basically, it's the absolute physical limit where a part will still successfully mate.
So let's break down the actual math here. For an internal feature, like a hole, we're usually dealing with maximum material condition because we want to guarantee clearance for a mating pin. The formula is beautifully simple. The virtual condition equals the MMC, which is the smallest allowable hole size, minus the geometric tolerance, like a position tolerance. And boom, that gives us the exact size of the go gauge pin we need to build.
Now, flip that logic for an external feature, like a shaft or a pin. To find the virtual condition at MMC here, you take the largest allowable size of that pin and you add the geometric tolerance. In this scenario, the virtual condition boundary grows larger, representing the absolute maximum envelope that pin is going to occupy in space. What's really fascinating here is how a geometric callout actively changes that physical envelope boundary we just calculated. Take a look at a perpendicularity tolerance of 0.4 at MMC applied relative to datum A. This means that as our feature reaches its maximum material condition, its allowable form and orientation variations are strictly capped, and that directly dictates the shape of the physical simulator we have to build to inspect it.
All right, Part 3, designing functional gauges, translating all this math into reality.
Okay, so we have the virtual condition math. How do we take these theoretical boundaries and actually cut steel to make a tool for the shop floor? The crucial starting point is knowing the difference between our two main types of functional gauges. Go gauges check the maximum material condition. They verify that the parts will mate. For a hole, the go gauge pin absolutely must fit into it. No-go gauges, on the other hand, check the least material condition. You typically use these to ensure enough material has been left for a further machining process, like boring. A no-go gauge must not fit into the feature.
Let's put this into a standardized 3-step design workflow. First step, you calculate the virtual condition straight from the print. Second, you apply what we call absolute gauge tolerancing. This is deliberately pessimistic. We apply our tolerances to the gauge so tightly that we will never, ever accept a bad part, even if it means we occasionally reject a part that's technically right on the borderline of being good. And third, we assign a geometric tolerance to the gauge itself.
And you've got to remember the 10% rule for that geometric tolerance. Your functional GeoGauge absolutely must be manufactured to be 10 times more accurate than the part it's checking. Why? Because the gauge itself is subject to manufacturing errors and thermal expansion.
If you don't hold the gauge to an incredibly tight tolerance, your whole inspection process becomes completely meaningless.
Part 4. Production workflows and examples. Let's inspect a bolt hole pattern.
Let's ground this in a real-world manufacturing workflow so we can see this exact process play out. Imagine we're checking a 15mm bolt hole pattern. The nominal hole is 15mm, with a really tight tolerance of plus 0.02. We've got a position tolerance of 0.2mm at MMC. So following our formula, the smallest hole is 15.0 minus that 0.2 position tolerance, which gives us a virtual condition of 14.8mm. Now, using our pessimistic absolute gauge tolerancing policy, we apply a positive tolerance only to the gauge. So we're going to machine our go gauge pins to be somewhere between 14.8 and 14.82mm.
But hey, functional gauging isn't just about a single pin floating in space, right? You have to include physical datum feature simulators. This means designing a physical fixture, like a chuck, a base plate, or locating pins, that completely constrains the part's degrees of freedom exactly the way it'll be constrained in the final assembly. The part has to sit cleanly in that datum simulator while the gauge pins pass through the holes.
Part 5. Functional gauges versus CMM, choosing the right inspection tool.
Now, you might be wondering, with all this talk about physical tooling, why not just throw everything on a coordinate measuring machine, a CMM, and call it a day? Well, this breakdown brilliantly illustrates where each method shines. Functional gauging is lightning fast, but gives you zero quantified data. It just says, yep, it fits, or nope, it doesn't. CMM inspection is relatively slow, but it gives you highly accurate deviation data, which is absolutely perfect for root cause analysis. Basically, you want your CMMs for low-volume production or first article inspections, but the second you hit mass production, you transition to functional gauges. Yes, they have a high upfront tooling cost, but the per-part inspection time drops to literal seconds.
Finally, Part 6, mistakes and key takeaways, or the common GD&T pitfalls you really need to avoid.
Before we wrap, let's rapidly run through the biggest design errors engineers make. Because if your GD&T is flawed on the drawing, your functional gauge is going to be completely useless. First, overcomplicating designs with super tight tolerances just to play it safe drives up manufacturing costs for literally no reason. Second, picking unstable datums or messing up the primary, secondary, tertiary hierarchy pretty much guarantees your part won't sit in the fixture properly. And third, confusing your material modifiers, like slopping LMC down when you definitely meant MMC, means all that virtual condition math we just learned will be totally wrong. And you'll end up scrapping perfectly good parts.
And here's a massive headache: using outdated or overly complex symbols. Take concentricity, for example. Did you know the ASME Y14.5 2018 standard actually just removed concentricity and symmetry altogether to stop the confusion? Inspecting concentricity required finding median points, which is a total nightmare for functional gauging. For physical mating parts, simple position or run-out tolerances are almost always the vastly superior functional options. I really want to drive this point home. GD&T is not the enemy of manufacturing. When you apply it correctly, proper GD&T actually opens up your tolerance zones by more than 50% compared to old-school linear dimensions. It gives the machinist way more breathing room and cuts down costs, provided it actually aligns with the real functional intent of the assembly.
So, to sum it all up for today's explainer, understanding virtual condition is the absolute key to proving your parts will actually assemble out there on the factory floor.
I'm going to leave you with this provocative thought. If your perfect, highly tolerant TAD model can't be quickly and reliably verified by a simple functional gauge on the production line, is it really a perfect design? Next lesson, CMM programming, measurement strategy, and GD&T inspection. Catch you then.